Hi, everybody. Thank you for joining this session. It's great to see so many of you. And my name is Emanuele, and I'm a data engineer for the OLX group. And I work in the Berlin Tech Hub. So what I want to share with you today is what we do at OLX, our approach to big data, but especially the experience of re-engineering our user notification data processing platform from a batch approach based on Redshift, so data warehouse, ETL pipeline, and SQL, to a near-time approach based on Python and Spark. So super quick introduction about OLX and how we approach big data. Overview about the user communication team, that is the team I work for, and what customer lifecycle management is, just to understand the context. Then we'll dive deep into our approach to near-time data engineering with Spark. Finally, a couple of takeaways, and hopefully there will be time for some of your questions. So our mission at OLX is that we fuel local economies by making it super easy for anyone to buy or sell almost anything through our platform. In other words, what we do is classifieds, right? So, and the main point for classified is to connect buyers and sellers and to facilitate win-win exchanges. In the classified world, there are two main platforms. There's horizontals and verticals. Horizontals are C2C, so customer-to-customer oriented, and buyers and sellers are normal users, and they go on this platform to pretty much buy and sell anything. And on verticals, on the other hand, they are more B2C, business-to-customers oriented, where the sellers are business companies, power users, and the buyers goes on this website, on this platform, to buy specific things like real estate or automotive. Of course, at OLX, we have both horizontals and verticals, and these are our brands. They all make up the OLX group, and the OLX group is part of Naspers. And as you probably know, Naspers is one of the biggest technology investors with shares other than in OLX, share in Tencent, Delivery Hero, Udemy, just to name a few. With all these brands, we operate in over 40 countries, and we serve monthly over 350 million people. Among these brands, you might recognize OLX brand, that is the biggest classified site in the world, with a presence over 35 countries. Letgo is getting super big in the US with over 100 million downloads. And for example, Avito, very big in Russia, and Dubizzle for the UAE. All the other brands are pretty much all verticals, and you might recognize AutoTrader, AutoVit, these are automotive verticals, or for example, ImmoVirtual and Property24 for real estate. If that still doesn't ring a bell, if you still don't recognize us, these are some of our numbers, right? And as you can see, we are quite sizable, right? We have a good presence all over the world with many brands, many offices. But looking at the bottom numbers, that's our data, right? That's what we care here. So through our platform, we do more than 1 million listings every day. Our users produce 4 billion events daily, and in the user communication team, we produce 50 million messages a day. So how do we approach big data? Of course, we start with the devices, and we have websites and mobile application. They produce these 4 billion events a day. They go in real time to our internal trackers that in micro batches, they write to our data lake. And our infrastructure is mostly based on AWS. So our data lake is built on top of S3, and right now it's 400 terabyte compressed. The little lock up there is to say that our data lake is locked down. Only few administrators, power users, can access their raw data there. And that's because of data privacy, GDPR, and these kind of things. For the other teams, in order to be able to access the data, we introduced the data catalog. And this is a tool where owners of these data sources can go there and publish the data sources. And any other team can go and subscribe. So it's a metadata catalog. And then we have in the middle these data pumps that are actually built with Spark streaming, that with a couple of minutes of delay, what they do is they take the raw data from the lake, they merge it with the metadata in the catalog, and they write data to what we call them reservoirs. And these reservoirs are mini data lakes that belong to a team. And this is how we do data democratization. So each team owns a reservoir, and each team can get the data they need to fulfill their purpose. The data in this reservoir can be a straight subset of the raw data, or could be pre-processed, like, for example, Parquet files with some field anonymized, again, for GDPR purposes, if you don't need the clear text. On top of this reservoir, we have teams building products, of course, BI, machine learning, and we have some proof of concepts running with Spark, MLlib, and analytics. And in the team I work for example, the user communication team, we build data products using Spark. In the user communication team, what we do is that we optimize and deliver OLX group and user communication. And we do this through the normal channels, so SMS, email, pushes. We have 3 types of messages. We have transactional messages, those standard messages you receive because you interact with the application. So you need to change a password. You need to, you receive a new reply to one of your listings. We have marketing messages. Of course, those messages craft and deliver to advertise specific initiatives. And for these 2 first type of messages, what we do in the user communication team is to give to our user the content creation tool and the delivery pipeline. We also have a 3rd type of message that you call Lifecycle, that is the core of CLM, of customer lifecycle management. And these are messages that are more complicated because they require more business logic, they require more data engineering. And the whole point of CLM is to try to keep the customer in the sweet spot. So we want new browsing user to go through the customer journey pipeline as fast as we can to convert this user to be buyers and sellers, so valuable user. But we also want to bring user back to the platform, user that might be inactive or lost for a while. You might wonder, why do I actually need a customer lifecycle management in first place? If you look at the first metric up there, this is valid for most applications. So 70% of a normal application user base is lost after 3 days. So if you do nothing, they're gone. With CLM, you can try to engage them, you can try to show them the value of your app, and maybe some of them stick around. The other 2 numbers there, they are very specific to us, and we have seen a 40% increase in daily active user and a 15% contribution to value-added service purchase, so to monetization. If you want to build a CLM service, a CLM system, you pretty much need all of these services: segmentation, recommendation, frequency copy, scheduling, and all of these services, they are data heavy. They require lots of data input, and they most likely produce data that is used by some of the other services. In the end, a CLM message, or how we call it, a treatment, is a combination of the data coming out of all these services to make decision about the user, their behavior, and send them the right message. The way we used to do it is using this kind of infrastructure, this batch approach. And all of you probably recognize this because it's a very common design pattern for data warehouse and BI. And of course, we would be loading the data every hour or every day when it's available. Data will sit in these data warehouses that in our case is Redshift, pretty much for the whole day. And next day, when the data was fully loaded, you will start with this long-running pipeline, this long-running job lasting 3, 4, 5 hours to do all the data crunching and preparing all the data for these services. And of course, there's nothing wrong with that. If what you do is BI, is data warehousing, there's nothing wrong. But we start seeing limitation, trying to make this one go faster, trying to go below 1 day, we start seeing limitation. And of course, lots of problem with the scheduler. So let's say that long ETL pipeline would break, hard to maintain, hard to debug. You need to rerun it will take a long time. And as well as most of the coding was done in SQL, so limitation with integration as well as introducing engineering best practices. So we start thinking, is there a better way to do this? Can we process our data from all at once a day, to a little each time, all the time? So instead of loading the data all at once, wait it there, and the next day process it, can we pre-process the data as soon as it comes in? Make the data ready for the next iteration as soon as possible. And while re-engineering and thinking about this way of processing data, we came up with these 4 pillars. We want our data processing to be near time, and we set ourselves a goal to send a message 10 minutes after a set of events happen. We want it to be open, so if our user, our stakeholder want to be more creative, experiment more, they have this crazy idea to interact with that API or use a machine learning something to be more, to do more, we don't want to be a blocker. We want it to be reliable, so we want to use technology and frameworks that allow us and make our life easy to implement best practices, testing, CI/CD, and all these kind of things. Finally, flexible. Big data is constantly changing, getting more complex, bigger all the time. We want a platform that can adapt easily to new data standards, new data regulation, and all of that. So how did we actually do this? Again, we start from our data reservoir that is based on an S3 bucket, where we receive from the pump we saw before our subset of raw data. Attached to this S3 bucket, we have a Kinesis stream. And every new file that goes into the reservoir, or every file that is changed, so is updated, because that happens to us as well, our raw data changes, the metadata goes into this stream. So the file name goes into there. Then we build this Kinesis consumer, that what it does, it's a Docker application running in Kubernetes, consumes the stream and aggregates all the file path, all the record into this task database. And here we introduce the concept of a data chunk. And you can think of a data chunk as a virtual partition, like 10 minutes of data, 5 minutes of data, right? It's something you can configure, something you can customize. So all we care about at this stage in this database is that we know that there is a data chunk going from A to B that needs to be processed at that specific time, 2-3 minutes after, just to allow for some delay. We forget here about the files that are in there, the size of the file. We just care about the data chunks. The centerpiece of the infrastructure is this feature processing application that is Apache Spark running on EMR, that when a data chunk is ready to process, goes back to the reservoir, pulls the data with regular expression that knows how to collect the data related to a specific data chunk, cache it, and I'm using that word now, and in parallel, create all the features attached to the specific data chunk. So we load the data once, memory, and in parallel, we calculate 10, 20 features, depending on our feature requirements. Then we write this feature to our output sinks. And of course, we have an offline store, that again is S3, and we write there Parquet files, partition with the Hive partitioning, and we use this for low-frequency data products, like segmentation. Segmentation, if it takes a little bit longer to run, is fine, because it needs to load a lot of data, needs to do a lot of aggregation and calculation. We have online stores for high-frequency data products, like the user mapping, the user device mapping service, because this service, in real time, needs to tell us all the devices belonging to a user. Everybody has a couple of devices this day, and we want to target a user in a consistent way across all his devices. We also have logical output stores, like a Glue data catalog, that if you're not familiar with AWS technology, is pretty much like Hive, where we publish all the external table attached to this feature and all the partition related to that table, so we can enable serverless analytics for our analysts to understand what's going on. If we look in the detail of, if we focus on the feature processor that is here in the middle, here how we build it, the software architecture around this. So there's a base object that is a processing core, that what it does is does a basic data handling. Loads the data, bit of configuration, bit of orchestration, and save the data. Then this object is extended by the engines. And what we mean with engine, we mean with reusable logic. So inside the engine is where we code our business transformation, our business logic. And what we realized pretty quick is that most of our features actually reuse a smaller number of engines. Let's say, take an example, number of posts and number of replies. What you're doing at the end of the day is counting actions. So what the feature is at the end of the day is just a pre-processing the data, selecting the right columns, filtering the right event, and sending it through the logic that is coded in the engine. So again, drier code, reusable, testable, and all these kind of things that we couldn't do in SQL, for example. Looking at the data flow, what you have on the left here is a representation of a data chunk. So 1120 to 1129.59. And this data chunk, this 10 minutes of data, is made of hundreds of files, 2-3 gigabyte for one of our smaller markets. When that data chunk is ready to process and accounting for some delays, could be 2-3 minutes after the timestamp, it goes through the processing, and we create a feature set attached to the data chunk. So attached to each data chunk, there's a set of features that is partitioned by the same partition of the data chunk. So in this case, 10 minutes. And again, this goes to S3, so our offline store, Parquet with the Hive partitioning. Another data chunk, another set of features. And here there's one interesting point. The feature is logically valid only inside the partition. Because if I count the number of posts, it's only valid inside that 10 minutes. If I take 2 partitions, 3 partitions, I need to aggregate them again, right? But this will come later in the process. The data product that uses those partitions will do that. One of the greatest advantage of this way of processing data is that if you look at this red square, red rectangle at the bottom left, this represents a late data or a piece of data that's been changed, that's been updated. And the way we are working, the way our upstream data processing works, this could happen even 6 months later. Because for GDPR, the user has the right to forget, right? The right to be forgotten. So what they do is that they go back into our raw data and they delete the user. If that happens, so if one of the file changes or one of the file is late, what we do is that we reprocess the whole data chunk. And because they are so compact, it's just a minute of data, and the bigger scheme of things, it's nothing, we can afford to constantly reprocess this data. And what we do is that we override and replace the feature in output. So that means that our features are the most accurate and the most consistent. And if you probably have noticed, there's no shadow here. It's all based on event, all based on the data coming in. And again, this makes the ETL constantly running much more robust. Looking in the details of what we just discussed, top screenshot is what our raw file looks like. And as you can see, they don't make our life easy because there's no partitioning. They are JSON, gzipped, so we need to work with that. The bottom one is what a record in the task database look like. And as you've seen here, we don't care anymore about the files. We just know that there's a data chunk that needs to be processed at that specific timestamp, and there's some information that we need to reconstruct the path, the regular expression to pull the data in. This is what the feature in output look like. They are Parquet file. Top one is user number of posts. Bottom one is user last login. Hive partitioning on the 10 minutes. If you see this feature, they are super compressed, right? They are mostly key value pairs, where the key for us is ID, country, and brand, and the fourth column is the metric we care about. And this is done on purpose because we want each feature to answer one question. We want this feature to be super atomic, right? If you need to do something else, something slightly different, we process another feature. It's fine. We can afford that. Looking at the piece of code, this is what the features look like. They look very similar, but they're actually different. So the one on the left says feature device last browse. The one on the right says feature user last login. And you can notice there, they both extend engine last action time. The difference there is that they select different columns and they filter different events. The one on the left, these are some browsing events, view item, view listings. The one on the right is login, sign in complete. And at the end, they expose, both of them expose 4 columns. But the one on the left says device ID as the first column, the one on the right says user ID. So you might wonder, how is that possible? It's because our engines, they are black boxes, right? They are self-contained. They define 3 things. They define an input schema, That is the data, this piece of code is expecting an input, and in this case, it's expecting an ID, a country, a brand, and a timestamp. And it doesn't really care if it's a device ID or a country ID or a user ID. Then it defines the transformation you want to run. In this case, it's a group by, ID, country, brand, find the maximum timestamp. But it could be something much more complicated. It could be a machine learning model that gets some data input and does some prediction in output. And finally, the output data schema. So what's the output of the data from this transformation? So what will be written in output? Here, an example of one of our data products, so Serverless Analytics. This one is a screenshot from Athena. And you can see here I'm querying a day of partition, doing some count distinct over millions of rows there, and it's running in 6 seconds, scanning 16 megabytes of data. That is much more less data than would have been if done on the raw data, right? So our analysts can't forget about the raw data. They don't need any more. They need a specific information. They request a feature for data engineering to be processed. Quick overview of our Spark environment. We 2.3.0 right now, Python 3, Spark SQL data frames, of course. We run on EMR, and we use R5 X-large instances. We found that they are memory optimized, and we found them very effective, especially for this kind of aggregations. And interesting thing is that on EMR, we can have this configuration where we have one master running, one slave that is called core, that has HDFS in it, and then a variable number of task instances. And task instances, if you're not familiar with AWS, they are lightweight core, so they don't come with HDFS, for example. All they do is processing the task. And we buy them on the spot market, so they are potentially 2/3 cheaper, and so we can auto-scale and use them as required. The other point I want to focus on is how we do continuous integration and deployment. So every time we push to master, there's a GitLab pipeline running. And what it does after running the test is packaging the code as an RPM. Then this RPM is pushed to an internal S3 bucket where we create an internal YAML repository, and we also build a little tool that is installed on the EMR cluster at Bootstrap. And what it does is periodically checking if there's a new RPM version available, download it, install it, and restart the service. Because our application, our Spark application, are actually Linux services that you can do service, start, and stop. Just to finish up, a couple of takeaways. Everybody was super happy to say goodbye to schedulers and having this new infrastructure just based on events, because we were really struggling working with schedulers. Our raw data is a bit messy and unpredictable, so we don't know when the data is fully there. So we've seen that constantly reprocessing the data as we do helps a lot with accuracy and consistency. A big point, especially on cost optimization, is the separation of storage and compute. Before, with Redshift, we had to have this huge machine always up just to keep the data there, and they would run for 3-4 hours a day to support these huge spikes, and they do nothing for the rest of the day. Now, the data is offline, is in S3. We just need some machine to run when we need to do the processing, and that's it. Finally, we really love the Python Spark combination because we saw that everybody could contribute to the project. Software engineer, data scientist, and even DevOps could embrace these frameworks and technology very easily and add their contribution, their value to the project. So I think that's it. Thank you very much, and I hope you enjoyed, and I think there's a bit of time for some of your questions.
Hi, thanks for the talk. You mentioned serverless analytics.
Yes.
I was curious, do you use anything for like dashboarding, reporting, or like what is packaged together with the serverless analytics? Like, is it all based on Athena, or do you use some other query engines on top of your S3?
So that's a very good question. As you've seen, we are migrating all those services from Redshift to something else, right? We are doing piece by piece. Analytics is still on Redshift for now. So our analysts to run ad hoc queries. They go on Athena, but our Tableau dashboard are still on Redshift. Again, we are planning to change that as well. We don't know yet.
Thanks again for the presentation. My question's also focused on analytics. So at the moment, well, in your initial architecture, maybe you processed once a day, and then that was it until the next day.
Yes.
And if something was wrong, it was wrong for a day.
Yes.
Right? In your new architecture, you're processing all the time, you're reprocessing, so something might be wrong, then get fixed again, or continuous improvement, continuous changes. If you have people downstream that are querying the results, then their results are changing every time you reprocess, I would imagine. Is that a problem? And
well, that could be a problem, right? But you would have that problem anyway. So what we are ensuring is that the feature, they are the most accurate at that point in time. Let's say that we have analytics, we have a BI thing downstream that they need to do aggregation over a month. And of course, those guys, they don't want the data to change, right? But let's say that there is some user information there that needs to go for GDPR. It needs to go, right? So the other services will need to adapt to this new way of processing data. But yeah, it's a point. It's one of the pain points of processing data this way.
So the Spark job, which picks up your raw data and processes it, is it a long-running job which is continuously polling your task database for new tasks to be executed, right?
Yes.
So your Spark job is essentially a very long-running job, which is every time a new RPM comes and it updates itself, it restarts itself.
No, so it's a long-running cluster. Cluster is always up, and we submit job constantly.
So the jobs itself are not long-running, but the clusters are.
Cluster is always up, right? Cluster is a long-running cluster, and to process 10 minutes of data is a matter of seconds, right? So right now, with a very small cluster, we are processing, as we are migrating, 2 hours of data in less than a minute.
Got it.
So 2 hours so 12 data chunks.
Well, thank you again. You mentioned about the GDPR right for the user to be forgotten.
Yeah.
Where in your architecture that the data can be removed from raw data. But also in GDPR, user has another right to object, where a typical case would be that the raw data could be there, but can only serve for specific purposes.
Yes.
For example, you can serve the raw data for business analytics, but you cannot serve it for personalized content recommendations, things like that. Is this something that your current platform have supported, or something you have a plan to put into consideration?
The picture you saw about our data platform was a simplified version, right? You may see that attached to the lake, there's a variety of tools. There's a tool that does the user deletion or to forget the user. There's also a tool that does the export of the user data if they're required to take away. Of course, there's all these requirements about you might need to keep the data for the government or for the police, right? But we don't care about that. So we are a big company. We have data engineering all over the place. For user notification, what we care about is that when you request to be forgotten, we don't send you messages ever again, right? So, but again, we are trying to open source this platform at least internally. So other teams might use the same platform in a slightly different way for the business reason. And for example, colleagues working in the fraud detection, they may need to keep the data there for longer because they have the purpose, they have the reason to keep it there in case there are investigations. Answer that question? Yeah, thank you.
That's all the time we have for questions. Thank you. And our next talk will begin in 10 minutes.